Hello, today we're going to take a look at continuity of functions. So by now, if you have watched my other videos, or if you are watching this, you definitely or probably already know the meaning of function. So here I'm going to define, so let's say the function, and I'm going to use the letter f. So I will say that the function f, make it darker, it's pretty light. So let's say I have a function f that goes from a domain, so we'll call D, goes to the range, and let's say in this case real number. Or sometimes you will see a function is defined as f that goes from Rn to Rm. So all it means is this goes from a domain to a range. In other words, behind the scene is pretty much like x-axis and y-axis. So the very basic definition, recall in all your calculus classes or Calc 1 and Calc 2, what is the meaning of a function? So let's take a look at the quick definition of function. So anytime, whenever you do any definitions in real analysis, advanced calculus, you want to start with let epsilon be greater than 0 be given. Then we're going to say f is, or the function f is continuous. So in this case, we're going to say continuous at a particular point. So I'll say continuous at C if there exists a real number delta greater than 0 such that the absolute value of the function itself, f of x, minus at that point, so what's the value of f is, so it will be f of c, is less than the given epsilon whenever or if the absolute value of x minus c, that's the point, is less than delta. So this is the definition you probably already know, you have been working with, and you definitely, going to use it going forward. So what happens if it is discontinuous? So this is a very basic one, then I'm going to go a little bit in detail because this video is all about just definitions and theorems that's related to continuous or continuity of function. So how do I know if it is continuous, discontinuous? So this may happen. So where can this happen? If you have a line, and then it may happen at an isolated point. So go and study isolated point, or ask me in your comment and I can give you another lecture on that. So isolated point in the domain itself. So we have a continuous function and then suddenly there's a hole there, so that will be not continuous. So an example, if you have a function on a, let's say x is rational, so 0 when it's rational, and then f is 1 when it's not rational, so you're going to go at two different points. Alright, now let's pay attention to continuous in this video, and I'll definitely try to do a video on not continuous. So let's see, continuous. So we know the definition from above. Again, let epsilon be greater than 0, then there exists delta greater than 0 such that the absolute value of f of x minus f of c less than epsilon whenever x minus c greater than epsilon. So this is called, I think some of them say local, so at a point. So in this case, you're going to say the definition is going to, your delta is going to depend on epsilon and the c, the point that you pick. So using the definition from above that we have up there, like right up here, so it depends on epsilon and c. So if it is 1 point, so what if it is continuous? So you're going to have two different points. What if it is in many points, more than 1 point? So we're going to take a look at this. What happens if you have on a set, and let's call that set E, and E is subset of your domain. Then in this case, we're going to say that delta is going to depend on, of course, all the points, right? So in this case, we'll say if it is continuous, if f is continuous at each x in the set. Whereas if you notice above here, at a point x has to be continuous only in that particular point. So we have, let's say I pick a point C. C is in that domain. Here is every x, so x1, x2, x3. So it's continuous in every point. Then finally, the other one is when you have on any x and y in the domain. So this will be called f is uniformly continuous. So uniformly continuous. So let me write the proper definitions of all of them. So we call a function is continuous, and I believe some of the books I have read, it says local or just continuous at a point. Then suppose in this case f goes from D to R, the domain goes to R, where you know D is a subset of R, of course. Then we will say f is continuous at x. So I'm going to pick a particular point, in this case x naught. So above here I said C, but here I'm going to do x naught in the domain if and only if this definition follows. So of course, as I said, always start with let epsilon be greater than 0 be given. Then there exists delta greater than 0 such that absolute value of f of x minus f of x naught in this case is less than epsilon whenever or if x minus that point is less than delta, and x naught must be in D. Well, the x value must be in D. It must be in your domain. What happens if I want to say it's continuous, but then I'm going to say in this time, I'm going to call it local or global. Earlier it's local. So in this case, again, we're going to let f go from D to R. So here we're going to say then f is continuous. So just see the difference. Where at or on a set E, that's a subset of the domain. So the biggest difference that we see here at a point and at a set, if and only if, oops, this happens. So if and only if, when f is continuous, if and only if, so we're going to follow all the rules up there. Let epsilon be greater than 0, then there exists delta greater than 0 such that f of x, everything is the 0, except we're going to say at each point on or in E. So x has to be continuous in every point. So that's called continuous globally. So the biggest keyword that you're looking is f is continuous at a point x naught, and then the other one is x is continuous on a set. Okay, so that's what continuous means here. And the last one that you need to know about continuous, they're going to throw in, of course, the word uniform. If they just say continuous, you want to watch if it is continuous at a point or continuous on a set, and they will just say f is continuous at every point. F is continuous at a point. Whereas for uniform continuous, what you're going to be told is this. So suppose you have a function, again f goes from D to R, we're going to be consistent here, and at D is a subset of R, of course, we will say that uniformly continuous on a set. So in this case, again, we want to let epsilon be a set in the domain. So we will say that F is uniformly continuous on E if and only if this definition follows. So we're going to say let epsilon be greater than 0. Then there exists delta greater than 0 such that f of x minus f of y is less than epsilon whenever or for all x comma y in E. Whenever, look at this, what's happening here? Whenever x comma y less than delta. So what is the biggest and main difference that you're watching, or you are, if you're paying attention? It's going to be that you do not have a fixed point and you're not picking all x in E, but you're picking any 2 points. No matter what 2 points I pick on my set in that domain, the difference of those set will be less than delta. And when that happens, then the difference of the range f of x minus f of y is always epsilon. So it's always consistent no matter what I pick, x and y, 2 points here, and then my epsilon is going to be f of x and f of y. So it doesn't matter where I pick my x and y. So whenever I do an example in the future, you're going to definitely come across this. Okay, the next thing I want to take a look quickly is going to be, because here we're just going to talk about theorems and functions, right? So let's rewrite or write the theorems clearly. So these are all definitions. Definitions of the local, definitions of global, definition of uniformly convergent. So now, of course, without theorem, real analysis doesn't really work, right? You need to prove all these theorems. In order to prove the theorems, you need to know the theorems. So let's take a look at theorem. So first one, what I have here is, suppose you must be given, right? If P then Q kind of deal. That's what proof is about. So suppose F is continuous. So you are told that F is continuous. And I'm even telling you where. On a closed and bounded interval. And we're going to call that interval A, B. So on x-axis, it goes from A to B. Both ends are closed. Then we're going to say F is bounded. So these are all the fun stuff that's going to happen when you find out F is continuous. In this case, suppose F is continuous on a closed bounded interval. Then F is bounded. Where is it bounded? Also on A to B. Okay, let's say what else can happen when F is continuous. So again, suppose F is continuous. So when they just told you F is continuous, you need to know continuous where. So here they're telling us F, remember F goes from D to R, because that's what's given in this particular video. So let's say if it is continuous on A comma B, if you see it's a closed interval, right? And there exists a real number K such that that K is between f of A and f of B, then we will say there exists a letter C which is on the domain AB, not including the endpoints, such that when you put your C into the function, it is actually the K that you just said it existed. In math, this is called, if you recall, intermediate value theorem. Okay, that's it for today. In the next lecture, I will probably talk about maybe mean value theorem and extreme value theorem. We're not going to talk about, sorry, no mean value theorem, extreme value theorem, and probably fixed points. But thank you for watching, and if you need me to look or do any extra examples, please put it in the comment. Thank you.